Hello, everyone. Now we're going to start covering section 6.3, cylindrical shells. So we're still trying to find volumes of solids, and we're still getting these solids by rotating them around a line. So we're still talking about these solids of revolution, they're called. But maybe we started picking up on this in the last section, that sometimes the disk and washer method is a bit difficult. So I've got two examples here of when disks and washers are difficult. Looking at this first example, let's try the disk and washer method. Okay, what would we do? Okay, I'm rotating around this y-axis. Okay, so that would mean if I was using the disk and washer method, I would want to do everything in terms of y, right? I would want to set up an integral like a to b pi. And then let's see, is it disks or washers? Well, here's the problem with this one. If I'm looking at the bottom part of this object, there's no empty space, right? It's just a solid object. Okay, so that would be a washer. Okay, but then I get to this part here, or excuse me, so the bottom part would be a disk. Okay, then I get to this top part, right? And there's empty space, so that would be a washer. So to deal with this object, I would have to kind of chop it up into two pieces where the bottom part would be a disk. Okay, and let's see, it would be I would measure that radius in terms of y, right? So it'd be like ry squared dy. And then I would have to, all right, so that would deal with the bottom half, and then I would have to do another piece for the top half that was washers. Okay, so I'd have to like have two integrals where one was disks and the other was washers. Okay, I've written it out kind of sloppy, but it's just an example. All right, and here would be another example of one that would be difficult to do with disks and washers. I have this object here, this 2D thing on the left, and I'm rotating that again around the y-axis. Okay, well, looking at the cross sections, they're always washers, right? Okay, so I don't have that same problem as before. But let's try and write an integral, just a real kind of informal integral real quick. See, I would be integrating from bottom to top. Okay, and it's washers. But what's my RO squared and what's my RI squared? Well, let's measure the radius on this left curve here. Okay, RO would be the distance from here to here. Okay, so that'd be like the let's see, the x coordinate of this curve, right? But the problem is, okay, when I go to do RI, well, it's the x coordinate of the same curve, right? So I only have one equation. Maybe my equation is, maybe this is like sine of x. Okay. So I have y equals sine of x, and I try and solve for x. Okay, and then I would get multiple x values for the same y value. It's unclear how I solve for x. So these are a couple examples of when disk and washer method might not be the best. So we're gonna, in this section, develop a new method called cylindrical shells. Okay. So let's look at the old method for a second. So let's consider this somewhat simple 2D shape here. Okay, and let's rotate around that y-axis to get this 3D shape. And let's look at how we kind of built up our disks and washers before, all right? I could, before I did an integral, I could think of it as chopping this up into slabs, right? Where I have these kind of thick slabs like this. Okay, and each one of these is either a disc or a washer, right? It's like if I kind of flipped it on its side, it would look like this. All right, it would be so this is kind of like a circular slab. All right, and if I looked at it from the top, it would look like this. Okay. So this is kind of the idea behind the disc and washer method. I chop my object up into these slabs to get an approximation. Okay. So if I added up all these volumes, I'll get an approximation to the volume of my white object, right? So that's the idea. And then the continuation of that is that if I make these discs, these slabs, skinnier and skinnier and skinnier, okay, my approximation is going to get better and better and better. Okay. So I started drawing these skinnier versions here and then kind of ran out of motivation. But we can see that if we made them skinnier and skinnier and skinnier, we'd get a better and better approximation. Okay. All right. And eventually they're going to be so skinny that they're basically just 2D discs and washers, right? And what are the areas of these discs and washers? Well, we know they have these formulas. Let's see. This is for disc and this is for washer. Okay. So that's the idea behind what we were doing in the previous section, right? We were taking these kind of slabs and making them thinner, and then we got to these 2D discs and washers. So that's where that method came from. Okay, but as we've seen, this method's got some problems. So let's develop a new method. So instead of doing stacked discs and washers, let's instead use nested cylinders, and I'll explain what I mean. Okay, so we're starting with the same 2D object and we're rotating around that same y-axis. But now instead of doing like solid discs stacked horizontally, okay, let's draw just a single cylinder. And let's kind of make it short and fat, this yellow cylinder inside my object. Okay, so that captures a little bit of the volume of my object, right? The good thing about these cylinders is that their volumes are easy to find. So this yellow cylinder has captured a little bit of the volume of my object. All right, and then let's kind of make it thin. Let's make the walls of this cylinder thin, and then let's put more cylinders kind of nested inside of it. Okay, so I have these colored cylinders that are inside my object, and if I add up all those volumes, that's getting pretty close to the volume of my white object, right? So that's the idea behind these nested cylinders. Okay, so real quick, okay, I've got some sort of 3D object like this. Okay, if I just wanted a real rough approximation to the volume, I could just do a single cylinder, right? And maybe it's completely solid. Okay, that would be an approximation to my volume. Okay, but if I want to make that approximation better, what should I do? I should make that cylinder thinner and put more cylinders inside of it. So maybe I have my 3D object again, okay? And maybe I'm making cylinders like this. Maybe I make one cylinder like this. Boom. Okay, and it's hollow inside. You know, it's a little bit, it's got a little bit of thickness here, but not too much. And then I do this blue cylinder inside of it, okay, to capture a little bit more of the volume. Okay, and the idea is I can make these cylinders thinner and have more of them, and eventually, okay, I have this 3D object, and I just have, you know, thousands and thousands of little cylinders, all very thin inside my object. So I have like a cylinder here, I have a cylinder here, and they're all kind of nested inside of each other. Okay. Kind of like Russian nesting dolls. And we see that as we make these cylinders thinner and nest more and more of them inside of each other, the approximation to my volume is going to get better and better and better. Okay, so that's the idea. All right. But to figure out what the volume is, we got to, just like with these slabs I used in my previous method, I had to be able to find uh, the volume of each of these individual slabs. Right? I needed a formula for these individual slabs. And then as I made them thinner, it kind of became the formula for a surface area, right? So I need to do something similar. I need to find the volumes of cylinders, of these approximating cylinders, okay? Well, let's forget about hollow cylinders for a second and think about this yellow solid cylinder here. What's its volume? Well, the volume of a cylinder is pi r squared times h, where r is the radius of that top, or that the bases, the top or bottom base, either one. And then h is the height of the cylinder, right? So this is basically the surface area of the base, and then this is like the height of the cylinder. Okay, so if we multiply the two things together, we get a volume of a cylinder. What about a hollow cylinder, which is kind of what we're going to be using? We're going to have these cylinders nested inside of each other. So each one has like some empty space here. Okay. Well, what would that be? It'd be the volume of the solid cylinder, right? The solid version of this cylinder. And then I'm going to subtract away the volume of the cylinder of empty space. Okay. So that's the idea. Okay, so its volume of this empty, or this kind of hollow cylinder, would be pi rho squared times h minus pi ri squared times h. So this would be like the volume of the solid cylinder, and then we're subtracting away the volume of the empty space. Okay, so we could write that in this compact formula like this: pi rho squared minus ri squared times h. All right, now, so this is my formula for volume of a hollow cylinder. Now let's just play with this formula a bit, and we're going to kind of rearrange it into something that's easier to work with. So starting here with what I had, same thing as what I had here, okay? We have pi rho squared minus ri squared, and then we can factor that rho squared minus ri squared, right? So just something we're going to use a lot in this class. Whenever I have a squared minus b squared, okay, whenever I see that, I should know automatically that's equal to a plus b times, excuse me, a plus b times a minus b, okay? So that's the fact I've used to go from here to here. All right, and then let's multiply this by 2 over 2, okay? So 2 over 2 is just 1, right? So multiplying by 1 doesn't really change anything, but I'm gonna rearrange these 2's to get something that makes some sort of geometric sense, okay? So let's bring this denominator over here. All right. Well, now I can think of this RO plus RI over 2. I can think of that as the average radius of my cylinder, okay? Meaning, if I look at this hollow cylinder here, it's kind of got two radiuses, right? It's got the outer radius, inner radius, okay? RO plus RI divided by 2. It's kind of like that radius right in the middle, the average radius, okay? Why is that important? Well, when I multiply by 2 pi h, that's going to give me basically the average, or like the surface area of my cylinder. And then this RO minus RI is like the thickness. So I have kind of like a surface area times a thickness. That's giving me my volume of my cylinder, okay? So that's how I think about this. All right. So I get, let's just rewrite this RO minus RI as this delta R. Okay, so maybe now it's starting to uh, look familiar as, the precursor to an integral. All right. All right, so this is the volume of a single hollow cylinder. And then if I look back at this idea of having nested cylinders, these cylinders inside of each other, giving me an approximation of the volume, if I add up the volumes of those cylinders, I should get an approximation of my volume. Okay, so this is just me adding up the volumes of those individual cylinders. So again, this is the volume of an individual cylinder, and then this is, our shorthand for adding up n cylinders, right? And then I want to, as I said before, my approximation is going to get better and better and better as I take these cylinders thinner and thinner and thinner and put more of them nested inside of each other. Okay. So as I take that limit, as the thickness of my cylinders goes to 0, what happens? Everything turns into an integral. So my summation sign turns into an integral sign. Well, 2 pi is constant, so that shouldn't change. Okay. My instead of having like a finite number of radiuses, I've got like an infinite number of cylinders, and it goes from an Ri to an R. Same thing with my height, and then my delta Ri becomes dr. Okay, so we've turned our summation into an integral, but let's look at what all this notation actually means. The 2 pi is just a constant, so there's no trouble there. What do the R, H, and dr really stand for? Okay. Uh, so a little uh, fact that we should be familiar with. Um, if we rotate around a vertical line, we're going to do everything in terms of x. So we're going to integrate in terms of x, and all our functions are going to be in terms of x. So that's the opposite of what we saw with disks and washers, right? And if we rotate around a horizontal line, we're going to do everything in terms of y, which again is the opposite of what we saw with disks and washers. So the dr is going to be either, it's really going to be a dx or a dy, depending on whether we're integrating in terms of x or y. Okay. All right. Now let's see what this radius and this height mean in our formula. Okay. So let's think about how we're drawing these cylinders. What I'm going to do is, okay, let's go back to our 3D object, and let's draw some of these cylinders. What I'm going to do is I'm going to start, let's see, I've rotated around a vertical line, right? Okay. So I'm going to do everything in terms of x. So let's keep that in mind. Okay. So let's measure out, let's kind of draw our cylinder like this. Let's first go kind of uh, perpendicular to the line I've rotated around. Okay, so I've rotated around this y-axis. So let's first go out at 90 degrees to that, and let's measure out our radius. Okay, so let's say I measure out this radius, and I don't have to go all the way to my curve. Okay, the idea is that I'm going to measure out a cylinder for every radius. So I'm going to have a cylinder that's like here, this wide, and then I'm going to have another one that's this wide, and so on. So I'm making these infinite number of cylinders, starting at my center line that I've rotated around, and then working outwards. Okay, so let's say I'm just thinking about this particular cylinder that's this wide. Okay, so I'm going to measure out this radius. Well, what is this radius? It's the distance from here to here, right? I'm trying to make this cleaner. Okay. Okay. This radius is this distance. Well, what is that distance? It's going to be, it's not really dependent on this curve, this object, okay? It's just whatever this distance is. Okay, so if this is my y-axis, then this distance is just whatever this x coordinate is, right? It's just that point on the x-axis. All right, so in this case, my radius is just x. Okay. And then once I've got my radius, I'm gonna turn and go up until I hit my curve, okay? And then this is gonna be my cylinder, right? Okay, so I've gone over, I've gone up, and then everything else is just drawing the other side of the cylinder, right? To complete the cylinder, I would then go straight across to the other side of my object, and then down, and then kind of back. And that's like the wall of my cylinder. And, this is gonna be a 3D object, so it's, this is actually a cylinder, okay, like that. All right. So what is the height of this cylinder? Well, it's whatever that distance is, right? So this distance, if okay, that distance is going to be the y coordinate of this point on my original curve, right? So remember that where this 3D object is coming from, we rotated this 2D object around the y-axis. So what I've done is I've started with radius, and then I've gone up until I hit my object, my curve, and then I've drawn the rest of my cylinder. But this distance, this height of this cylinder, is going to be, in this case, it's going to be whatever the y coordinate of this point on the curve is. Okay. And usually we're going to have some equation that gives us the y coordinate in terms of x, right? So it's whatever that equation was. So that's what we've drawn here. I've just done the same thing here. Okay. I've just done it in green. Okay. So the radius is typically going to be some simple function of our variable, whatever variable we're using. It might be as simple as the radius is equal to x. It might be something like, if we're integrating in terms of y, it might be something like y plus 1 or x minus 2, but it's going to be usually pretty simple. And then the height is going to be coming from the equations of our original 2D object. So again, it might be something as simple as just, okay, it's just, the height is just that y coordinate, just that f of x. Or it might be something more complicated like f of x plus 1 or f of x minus gx, depending on what kind of curves are involved and what line we're rotating around, okay? What line we're rotating around is also going to affect this stuff up here. So that's the idea, all right? So we're going up to these cylinders. The radius of the cylinder is usually going to be something simple like x, and then the height of the cylinder is going to be something like f of x, okay? And I'm going to lay out some concrete steps to help you figure out these things. So now let's talk about the steps. Let's talk about how to do this in practice, and then we'll do several examples to hopefully hammer home how to do this stuff. All right. So we're going to always start by drawing our 2D region, right? And then we're going to rotate it. Step 2 would be to rotate it around whatever line we're given. And remember these guidelines. If we're rotating around a vertical line, everything's going to be done in terms of x. Okay, so if we rotate around a vertical line, we need to be integrating in terms of x, and all our functions inside the integral need to be in terms of x. If we're rotating around a horizontal line, it's the opposite. It needs to be in terms of y. Okay, and remember, this stuff is the opposite of the disk and washer criteria, right? So different method, different rule. Okay. And then step 3, I would suggest sketching a cylinder and trying to get an idea of what one of these approximating cylinders looks like. It's going to really help in finding the radius and height of these cylinders. Okay, and that's what step 4 and 5 are. 4, find a radius function, and we're measuring the radius from the line we've rotated around. Okay, so don't measure it. It's not necessarily always going to be measured from the y-axis or x-axis. It's measured from whatever line we're rotating around. And then the height is going to be determined by the curves we started with in our 2D region. So that's step 5, finding the height. Finding the bounds of integration. We're going to integrate again from that line we've rotated around, that center line outward, and we're only going to do it in one direction. My favorite band. So we're going to start at the line we rotate around and work our way outward in one direction. And then we're only going to use bounds where our object exists. Okay, so I'll explain that when we get to it. It might not make sense now, but hopefully if you revisit these steps, everything's going to make sense. After step 6, we have all the information we need. We have our bounds of integration. We have our functions that we're integrating. So step 7 would just be to write out the integral and integrate. So now let's try and apply these steps to this problem. This is number 3 in the textbook, I believe. So let's start with the 2D region given by, enclosed by these curves. Okay, so enclosed by y equals cube root of x, y equals 0, and x equals 1. And let's take that 2D region and rotate it around the y-axis. Okay, so let's go through our steps. Step 1, drawing our 2D region. Okay, I've done that here. Okay. Step 2, let's try and rotate it around the y-axis and draw our 3D region. This will cooperate. Okay, so we draw our 3D region and we get something like this. And then let's try and draw one of our approximating cylinders, right? Okay. So that would be step 3. Okay, so this is our 3D object. And what would one of these cylinders inside of my object look like? Well, let's see. Since I've rotated around a vertical line, okay, when I draw one of my cylinders, what am I going to do? I'm going to start at the line I've rotated around and go outward. Okay, so that first step would be like, okay, go into here. Okay, so maybe I have a cylinder this wide. Okay, and then I turn and go up until I hit my curve. Boom. Okay, and then my cylinder just wraps all the way around my object. Okay, and it's symmetrical, right? Okay, so this is my cylinder. Step 4, I need to start finding my information about this cylinder. Let's start with radius, okay? So let's look at this green cylinder. I drew it from here to here. What's the radius of that cylinder? Well, since this is the y-axis, the radius is just going to be whatever this x coordinate is, right? Okay, so r of x equals x, okay? All right. What's the height? Okay, and maybe it'll be helpful to kind of go back to our original 2D region to find this height. Okay, so let's say I drew a cylinder, kind of pictured on the 3D object, but I started here at the y-axis, I went out to here. Okay, so that's my radius, and then I went up until I hit my curve. Okay, so what is this distance? What is this height of the cylinder? Well, since this is the x-axis, this distance here is going to be whatever that y coordinate is, right? That y coordinate on my curve, which is given by what? This is the curve cube root of x, right? Okay, so my height should be the y coordinate on that curve, which is given by y equals cube root of x. So my height in terms of x is just cube root of x. Okay. So I have these two pieces of information. I got my radius in terms of x, and I got my height in terms of x. Number 6, step 6. I need to find my bounds of integration. Okay. So I'm adding up the volume of all these cylinders, and as they get thinner and thinner and thinner, it becomes an integral. Where am I integrating? I'm starting at the line I've rotated around, my center line, and I'm rotating outward. Okay, so I would start here where my center line is, and I would rotate outward until my object ends. Okay, so I only want to integrate along my object, the center of my object to where my object ends. Okay, so what are these points? Well, this would be x equals 0, and then what is this point? Well, that vertical line was x equals 1. Okay, so I want to integrate from 0 to 1. Okay. Number 7, step 7. Okay, now I've got all the information I need to form my integral. Okay, so my bounds are 0 to 1. I got my 2 pi. I always have my 2 pi. What else do I need? I need radius, height, and then dx, dy, whatever the appropriate d is. Okay, so we said our radius function was just x. My height function is cube root of x. And then I have my dx because I'm integrating in terms of x. So this is my integral. Next, I just need to solve my integral, right? Okay, well, the 2 pi is constant, so I can bring that outside. And then I have x times cube root of x. Don't overthink it, okay? So I got 2 pi. What's cube root of x? How could I rewrite that? That's the same thing as x to the 1/3, right? So I got x times x to the 1/3. So that's x to the 4/3. And then it's a fairly easy integral, right? It's just the power rule. Okay, so x would be x to the 7/3 divided by 7/3 from 1 to 0. Okay, so I have 2 pi times 3 over 7, x to the 7/3, power of 7 over 3 from 0 to 1. Okay, so plugging in 1, I get 1. Plugging in 0, I get 0. So my answer is just, let's see, 6 over 7 pi. And that should be my volume. All right, so now let's just see some slightly more complicated examples of applying these steps. Okay, so all we got to do is apply these steps, and I'll try and show you some more complicated examples of how to do that. Okay, now let's look at, how about number 11 in the book? So this time, let's start with the region enclosed by these curves. And instead of rotating around the y-axis, let's rotate around x-axis. So right away, I see that I'm rotating around a horizontal line. So everything I do, it should be in terms of x, or excuse me, y. All right. So let's draw our region first of all, our 2D region. Okay, so if I draw my 2D region, it should be this thing on the left. Okay, this blue shaded area. This curve here would be y equals x to the power 3/2. This is just a line y equals 8. And then we have this bound on the left given by x equals 0. Okay, so that's our region. And then let's go ahead and rotate it around the x-axis. Okay, so I'd get something like, okay, it'd be kind of very similar to the previous shape we had before. just kind of turned on its side. So kind of a sideways bowl. All right, and then, so this would be step 1 and 2, and then let's try and draw one of our cylinders. Okay, so let's just, boom, let's bring that here. One of our cylinders, let's do it in blue. Let's see. So I've rotated around this x-axis. So my radius I should measure going this way, okay? And let's say I just measure to here, okay? And then what would I do? I would draw my cylinder until I hit my curve. Well, that's the kind of interior wall of my curve, right? And then my cylinder would wrap around like this. Okay, so that would be my cylinder, all right? Now let's try and figure out my height, my radius, height, and so on. Okay. So radius. Okay. Let's go. I like always doing this on my 2D object. So let's go back up to our 2D object, and let's say I've drawn my radius to here, and then I've gone out to here. Okay. What's my radius, first of all? Okay, it's just this distance. Okay, so, well, this is not determined, it's not determined by the curves at all, it's just the distance from here to here. Okay, what is that? Well, since this is the x-axis here, I just have this distance is the y-coordinate on that x-axis. Okay, so my radius is just going to be the y-coordinate. Okay. And then what's the height of my cylinder? It might seem weird to call it the height because it would actually be, I guess, more like the length of our cylinder. The length of our cylinder is this distance, right? Okay. Well, what is this distance? It's the distance from the y-axis to this point. Well, that's just the x-coordinate on my curve. Okay. What curve is that? That's the y equals x to the power 3/2, right? So we have this equation, and I'm looking for the x coordinate. Okay, so when I know the y, what is the x coordinate? All right, so I just take this equation and solve for x. Okay, so this should be my radius. Okay, I should have y to the power 2/3 equals the height of my height or length of my cylinder. Okay. Now, step 6, my bounds of integration. Okay, so again, I want to integrate along my object. So let's again go back to the 2D version. Okay, I want to start at the center line and move outward. Okay, so let's say I start here and then I integrate upwards. Where do I stop? Okay, I stop at where my object ends. This is the line y equals 8. So I want to integrate from y equals 0 to y equals 8. Okay. So now I have all the information I need for my integral. So I got my 2 pi as always. What's my radius? My radius is just y. What's my height slash length of my cylinder? That's y to the power of 2/3. And then I'm integrating in terms of y. Okay. Now I just need to integrate. So pull out the 2 pi. Y times y to the power 2/3 is y to the power 5/3. And then it's just power rule. Okay, and then it's just evaluating this integral, which should be, oh God, it'd be 6 pi, let's see, 8 to the power of 8 over 3 is 2 to the power 8, which would be, let's see, I think 256. And then I plug in 0, I get 0. So simplifying that, I should have 6 pi times 32, I believe. So let's see if it's 192 pi. And it is. All right, so that is that problem. Now let's try just one more example. I'll save the rest of the problems for the problem video, but let's do one example of something a bit stranger. So let's try and do number 18 from the book. So let's start with the 2D region enclosed by y equals square root of x equals 2y. Then let's rotate that region around x equals 5. So the region should look, the 2D region should look something like this. Okay. This curve here is square root of x, and then x equals 2y. Well, that's the same as y equals x over 2. So that'd be this line here. And so there should be a region like this. Okay, this shaded region. And then we're going to rotate that around the line x equals 5. Okay, so where is the line x equals 5? That's, out here maybe. Okay. So let's try and get the 3D picture of what's going on. Okay, so let's see, I would rotate this around that dotted line and I'd have some sort of kind of mirror image. Maybe it looks like this. And then my 3D object would be, excuse me. My 3D object would be something that looks like this. Okay, I've made an attempt at drawing a 3D shape. It'd be kind of like a dome with a hole in the top, kind of like a volcano, I guess. And then all this is empty space, and the walls of this thing are just these kind of the solid walls of this are just really kind of thin. So this whole base is just empty space here. Okay. All right. So try and keep that pictured in your head. All right. Step 3, drawing one of our cylinders, right? Okay. So let's see. How do I want to draw my cylinder? Let's draw it in blue. Okay. So I want to start at the center of the line I'm rotating around, and then I'll always draw my cylinder kind of going back to my original, towards my original 2D region, which is like this piece, right? All right. So let's see. I want to start drawing my cylinder. And I'm going to go and I'm going to go until I hit the bottom of my curve, okay, or the bottom of my object. Okay, so in our previous cases, our object was like along one of the axes, like it had kind of a solid bottom. So like I would start here and maybe draw until I, wanted to stop my radius, and then I would just go up until I hit the top of my curve. Okay, but when the object looks like this, how should we draw our cylinders? I'm still going to start at my center line. And I'm going to draw until I kind of hit a solid wall of my object. Okay. And then I'm going to draw up until I hit the kind of roof of my object. Okay. And then my cylinder would wrap around. Okay. So the cylinder doesn't have to be sitting right on the axes, okay? So this would be one cylinder, and then maybe I'd have, another cylinder nested inside that I drew like this, okay? And then it goes up a bit further, okay? So these cylinders don't all have to be on the same level, is what I'm trying to say. They are nested inside of each other, but they don't all have to be sitting on the x-axis or anything. Okay, so those are what our cylinders might look like. All right, so let's focus on one, and let's go up to this 2D object. Okay, maybe it'll help to visualize it like this. So I start on my y-axis, and I go until I hit the bottom of my object, and then I go up. Okay, so what is this distance? What is this radius? All right, that's what we're trying to find now. Well, I guess we've kind of drawn our cylinders up here, and now step 4, let's try and find our radius. Okay, so what is this distance, this blue horizontal distance? Well, let's see. If it was this entire thing, well, that would be 5, right? Because this line is at 5. Okay, but we need to subtract away whatever that distance is. Okay, so what is that distance? That's the x-coordinate on my curve there. Okay, and what curve am I referring to? I'm referring to the line. Okay, because that's where my radius, is measured to. I measure it to the bottom of this object, which is this little white dot, and then I go up. Right. All right. So this white dot is at a point on the line x equals 2y. Okay. So what's that x coordinate there? Well, let's see. It's going to be 2y. Okay, so it's just that. So my radius in terms of x should be 5 minus 2y. Oh, and really it's just going to be 5 minus x, right? Because we want to do everything in terms of, since we've rotated around a vertical line, we want to do everything in terms of x. Okay, so our radius is just going to be 5 minus x. Okay, so we don't even need this stuff yet. All right. And then what's the height of my cylinder? Okay, now let's do that in, let's say, green. And let's still work with this 2D shape. Okay, so I've drawn my radius up to here, boom. And then what's the height of my cylinder? Well, my cylinder would then go up until I hit the roof of my object, and then it would kind of loop back around. So what is this distance? Okay, well, it's going to be this y coordinate minus this y coordinate. Okay, so what are those y coordinates? The top curve, remember the top curve is y equals square root of x, and then the bottom curve is x equals 2y, which we could write as y equals x over 2. Okay, so the y coordinates are these. All right, so this is the top y coordinate, this is the bottom y coordinate. So that height should be square root of x minus x over 2. All right, what are my bounds? Okay, and this is a good example to show what I meant in my steps. When we laid out our steps, we said find the bounds of integration, start at the center of the object, go outward in one direction. Only use bounds where the object exists. All right, so this is kind of what the critical point I want to emphasize. All right. Okay. So where should I integrate? I'm going to only integrate in one direction. And I said start at the center and go outward, but really starting at the center is not necessary. We could end at the center as well. So let's say I'm going to start here at x equals 0, and I'm going to integrate inward. And then I would stop at, I wouldn't go past 5, okay? But I might not go all the way to 5 either. So if I integrate, let's see, I should stop integrating here, right? Because past this line, my object no longer exists. So there's no volume in this region, okay? So really my bounds of integration, okay, should be from x equals 0 to whatever point this is. So what point is this? That's where these two curves intersect again, right? So x equals 0 is one, and then to find the other, I need to set square root of x equal to x over 2. That was that other curve, right? And then let's solve for x. Let's see, how do I solve for x? I need to get rid of that square root so I can square both sides. Okay, and then let's get everything to one side of the equation. Let's factor. All right, and then this has solutions x equals 0, x equals 4. All right, so we already knew this one. We already saw just by inspecting our graph that the curves intersect at 0. And then this is the other bound, x equals 4. So my bounds of integration need to be from 0 to 4. And now that's enough information to form my integral. My integral should be 0 to 4, 2 pi. What's my radius? We said our radius was 5 minus x. What's our height? It's going to be square root of x minus x over 2. Okay, and now I just need to integrate. So I'm going to pull my 2 pi outside. Okay, and then I need to multiply this stuff out, FOIL it out. Now I need to integrate. Okay, so it's kind of ugly. So let's go ahead and plug in our values. Let's see, I get 10 over 3 times 8 minus 20 minus 64 over 5 plus 64 over 6. All right, simplifying that fraction, that all this stuff inside should be equal to 26 over 3, I believe. So our final answer should be 52 pi over 3. Okay. Unless I've made some horrible mistake somewhere. So this problem's definitely difficult, but keep in mind these points when talking about the radius of your cylinders and the height of your cylinders. All right, so keep in mind how we found those radius and heights. All right, and if you need more examples, that will follow in the problem.